calculation of electric potential. So whenever we have to calculate electric potential, we will go with the very basic or fundamental relation as we have derived earlier or defined. If change in potential is given as change in potential energy per unit charge, or we can write delta V is your delta U by Q naught. This is the one of the fundamental relation, and another relation is the electric field relation. dV is your minus E dot dr. Any of these two relations can be used to determine the potential due to different charge body. So let one by one we will consider different cases. First, potential due to point charge. So potential due to point charge. Let a point charge Q is kept here, and we want to calculate potential due to this charge at different point of potential difference between these two charge at point 1 and 2. So let point 1 is at distance r1 and point 2 is at a distance r2. Now there are two ways. Either we can go with this relation or we can go with this relation. Any way we can solve. So see, this is the one case we will in which I will discuss both the cases. So what is the meaning of delta V delta U by Q naught? It means if we want to calculate potential between 2 and 1 point, any potential difference between 2 and 1, V2 minus V1 is nothing. It is equal to your potential energy at 2 minus potential energy at 1 by Q naught, and Q naught is the test charge. So here first I would like to put a test charge at point 1 and then 2, and we will calculate the potential energy at 2 and 1, and we can write here. If I am putting the test charge at Q naught, then see what is the potential energy at 1. U1 written as 1 by 4 pi epsilon naught Q naught by R1, and potential energy at point 2 1 by 4 pi epsilon naught Q naught by R2, and substitute this. So we will get V2 minus V1 is 1 by 4 pi epsilon naught Q 1 by R2 minus 1 by R1. This is the potential difference between the point 2 and 1. Similarly, if we are following this method, similarly see, as due to point charge electric field value we know, and electric field is inversely proportional to distance. So from 1 to 2 electric field value is variable. So we will assume any point, intermediate point, which is at distance r from the charge Q. Here we will calculate electric field. So for a small distance dr, how much field? See, so dV for a small distance dr written as minus E dot dr, and minus E value for at this point. Here no need of any test charge. So E value due to this charge is your Q by R square dr, and now integrate. So here point 1 in V1 to V2. So it will be your V2 minus V1, which you will get 1 by 4 pi epsilon naught Q 1 by R2 minus 1 by R1. The same method as we have followed, the same expression we will get as here. Now, as potential energy means potential is due to the interaction between the two charges, because potential energy is due to the interaction. So when the charges are at infinity, there is no interaction, so we can say there is no potential. So for that we can define one point as a infinity for reference. So let if R2 is at infinity, R2 is infinity means 0.2 at infinity. So potential corresponding to R2 means 2 is written as V at infinity, and R1 is at a distance R. R1 means 0.1 at a general point R. So V at 1 written as V at R. So our expression, we can replace this value in our expression, any of the expression. So V2 minus V1, 2 means V infinity, V1 means VR. So V infinity minus V at R, 1 by 4 pi epsilon naught Q, R2 your infinity, R1 is your R, so 1 by infinity minus 1 by R. So VR is V at infinity plus Q by R. This is the general expression for a potential due to point charge. So normally we are representing potential with respect to infinity. So 1 by 4 pi epsilon naught Q by R. So if nothing is given in the question here, it means we have to put the V infinity as 0, because at infinite there is no interaction between the charges, so no potential. And if in some of the question they are writing, okay, assuming potential at infinity is this much, so we will write the potential at infinity value here and we will use this our expression. And since our potential is your defined with a potential energy and it is your scalar, so our potential is also scalar, so the charge value also we have to put according to their sign. A positive charge, positive value of charge, a negative charge, so we have to use negative sign. So this is the potential due to point charge. Now if we are having a distributed mass or point charge is not there, then we can use principle of superposition to determine potential due to charge bodies. Now see the next point. Second point, potential difference due to long line charge conductor. Line charge conductor. So let we are having a long conductor and lambda is the linear charge density. Lambda is linear charge density. Okay. Now due to this, if we want to find potential difference between any 2 points, let point 1 and 2 if we want to calculate. Point 1 let at distance R1 and point 2 at a distance R2. So we are following let this method. dV is equal to your minus E dot dr. So electric field due to line charge conductor is given as electric field is given as lambda by 2 pi epsilon naught R. So electric field your variable with position. So at any certain point, here we are assuming let taking the element at dr. So dV between these 2 points. So dV written as minus lambda by 2 pi epsilon naught R dr. Now integrate. So we are moving from 1 to 2. 1 means potential 1 R1, 2 means potential at point 2 R2. So V2 minus V1 is minus lambda by 2 pi epsilon naught ln R2 by R1, or V1 minus V2 is lambda by 2 pi epsilon naught ln R2 by R1. This is the potential due to long line charge conductor. So, potential difference this. Important point here, R2 cannot be infinity. It means potential difference with respect to infinity cannot be defined. It means because this is your undefined, it means potential difference with respect to infinity cannot be defined. So, in this case, in this particular case, cannot with respect to infinity cannot be defined. So, that indicate, or that we can say, the potential difference due to long line charge conductor is defined only for finite distance. It is not defined for with respect to infinite point. Now, next is the potential on the axis of charge ring. Potential on the axis of charge ring. Let this is your ring and it has charge Q and radius R, and we want to calculate the potential at point P, which is on its axis, and let that point P is at R distance away from the center of the ring. So, here this is our charge distributed body, and as already we have calculated potential due to point charge. So, as we know, potential due to point charge is given as potential due to point charge. We can write here 1 by 4 pi epsilon naught Q by R. So, here this ring can be taken as a number of point charges kept on the circumference of this ring, and then we can apply principle of superposition by simple algebraic superposition, because potential is your scalar quantity. So, I took here a small element having charge dq, and this is the distance of that element from point P, and this is equal to R square plus R square. So, potential due to this small element dV is written as 1 by 4 pi epsilon naught dq by root over R square plus R square. It is just like a point charge, charge by distance here, charge by distance. Now, total potential, integrate. Total potential if we are calculating, so 1 by 4 pi epsilon naught dq by R square plus R square. So, integration of dq become a total charge q. So, total charge q will be like this, q by root over R square plus R square. This is the potential on the axis of ring, and which is given as 1 by 4 pi epsilon naught q by root over under root R square plus small r square. Potential on the axis of uniformly charged disk. let this is your disk and it has charge Q, radius R. The sigma is your charge per unit area or charge per unit area. Now, if we want to find the potential at point P, which is distance R from the center of disk, so what can be taken here? This disk can be taken as a concentric rings kept one over another, and due to ring already we have determined the potential. So, see, if we are considering a ring of radius y and thickness dy, so dq is the charge on that ring and it is given as sigma into 2 pi y dy. Due to this ring, here potential we can get, which is your y square plus r square, the distance. So, due to this ring, potential at point P, dV is 1 by 4 pi epsilon naught dq by root over r square plus y square. Now, substitute the value of dq. So, dV is 1 by 4 pi epsilon naught, dq means here sigma 2 pi y dy r square plus y square. The sigma by 2 epsilon naught y dy by, now integrate y, the limit of y from 0 to capital R. See how we can integrate here. To take y square plus r square, let it is your t square. So, y dy will be your t dt, and now we can solve. So, v is your sigma by 2 epsilon naught y dy, if I am writing t dt, root over y square plus r square become your t, and limit of t when y was 0, when y is 0, so t is equal to your r, and when y is your capital R, so t will be your root over r square plus r square. So, potential will be your sigma by 2 epsilon naught, and this is your r square plus r square minus r. This is the potential on the axis of ring, and V is equal to sigma by 2 epsilon naught under root of r square plus r square minus r.